So in today's video, I'm going to explain you some basics of Maxwell's equations and give you some idea about the Maxwell's equations, their integral and the differential form, and their physical significance. See, this is the topic which is widely used in engineering, right? Either in electronics and communication branch or in engineering physics branch or in any other branches, right? So this is the widely used topic. So I thought that I should make a video on Maxwell's equations, right? See, in 1864, Maxwell's combined four basic law, that is Gauss law in electrostatics, Gauss law in magnetostatics, Faraday's law, and Ampere's law. Maxwell's combined these four basic law, right, and named it like Maxwell's equations, and made some correction in the Ampere's law, that is basically later on known as the modified Ampere's law, basically. So before going into the details, I would like mention here that Maxwell's equations, they are used in integral as well as in differential form, depending upon the problems to be solved. Okay. So these are the outline of today's video. Maxwell's equations, right? Differential and integral form of Maxwell's equations, physical significance of Maxwell's equations. So four basic laws, as I told you earlier, that these are the basically known as the Maxwell's equations. The first one is the del dot E equals to rho upon epsilon naught, right? Divergence of electric field is equals to rho upon epsilon naught. This del is having a differential operator, is having a value I del over del x, j del over del y, and k del over del z. So this quantity mathematically is also known as the divergence of electric field is equals to rho upon epsilon naught, where rho is the charge density, right? Volume charge density, I should say. So this one is known as the Gauss law in electrostatics. The second equation is the divergence of magnetic field is equal to 0. This one is known as the Gauss law in magnetostatics. And the third one is known as basically del cross E, the curl of electric field is equal to with minus sign of rate of change of magnetic field. So basically this one is known as the Faraday's law. And from this equation, you clearly, you can see that a change in magnetic field can produce the electric field, basically. And the fourth one is del cross D, that is the curl of magnetic field is equals to mu naught J plus mu naught epsilon naught del E by del T. Basically, this one is known as the Ampere's law, or I should say modified Ampere's law. So Maxwell modified this Ampere's law. Before the modification, the law was just del cross B equals to mu naught J. But this law was not fully applicable for non-steady fields. But here Maxwell made some correction in Ampere's law, which is now known as the modified Ampere's law, by introducing the concept of displacement current. So this additional term mu naught epsilon naught del E by del T is known as the displacement current, right? So now this equation, that is Maxwell's fourth equation, is applicable now for both steady and non-steady fields. Okay. So basically, I would like to tell you something about the displacement current. So what is the displacement current? So this additional term, which I told you that mu naught epsilon or del E by del T is known as the displacement current. You can see here, right? JD is equals to epsilon or del E by del T. So you can see from the formula that this displacement current density is basically producing because of rate of change of electric field. As long as this electric field is changing with the time, you are getting the value of displacement current density. And when it becomes constant, if electric field is not changing with the time, for example, if electric field is constant, in that case, this displacement current density does not exist, right? And JD basically is equals to ID upon A. Current upon area basically is known as the displacement current density. So you can see here ID is equals to, okay, JD into A, that is epsilon naught del E by del T, right? And further we can write here epsilon naught d phi by dt. This phi is basically electric flux. So phi E is basically equals to E dot A, electric field into area. This is known as the electric flux basically. Okay. So see, displacement current play a very crucial role here to understand the Ampere's law, and it has many applications in electromagnetic field theory. So the concept of displacement current was first introduced by the Maxwells purely on the theoretical ground. Okay. So to understand this, the concept of displacement current, Maxwell's explain the charging of the capacitor. Okay, and with the help of that charging of the capacitor, he explained the concept of displacement current. See, so I will share a different video for the displacement current and the modification of Ampere's law. So in today's video, I will concentrate mainly on the Maxwell's equations. Now this is the integral and the differential form of Maxwell's equations. You can see here, this one, first one is the E dot ds. Basically, this one is known as the electric flux. So it says that the electric flux through any closed body should be equal to 1 upon epsilon times into total charge enclosed by the surface. And its differential form, I already told you that divergence of electric field is equals to rho upon epsilon naught. What is rho? Rho is volume charge density. Okay. The second equation is B dot ds, that is the magnetic flux through any closed body should be equal to 0, and its differential form is del dot B is equal to 0. Third one is the line integral of electric field is equals to minus sign of rate of change of magnetic field, and its differential form is here. You can see del cross A is equals to minus del B upon del T. The fourth one is that, which is known as the modified Ampere's law, B dot dl is equals to mu naught J plus epsilon naught del E by del T into ds, and its differential form you can see here, del cross B equals to mu naught J plus epsilon naught at del E by del T. All these four equations, they have their unique significance, and whole electromagnetic theory can be explained with the help of these four Maxwell's equations, right? So the significance of Maxwell's equation is here, that you can see here that the first significance of Maxwell's first equation is the electric flux through any closed body should be equal to 1 upon epsilon naught times into total charge enclosed by that surface. Basically, this one is known as the Gauss law in electrostatic. Electric flux through any closed surface is equal to 1 upon epsilon naught times the total charge enclosed by the surface. So this one is known, basically, this one is known as the Gauss law in electrostatics. The second equation you can see here, the magnetic flux through any closed body is equal to 0. This one is the Gauss law in magnetostatics. Okay. So it says that the magnetic flux, it means if you are having a magnet, the magnet must have two poles, south pole and the north pole. Okay, then only it is possible that the flux, magnetic flux through any closed body should be equal to 0. Okay, it signifies that monopole does not exist. That is the significance of Maxwell's second equations, right? Monopole does not exist. So this one is the Gauss law in electrostatic, Maxwell's first equations. This one is the Gauss law in magnetostatics, right? And the third one is the line integral of electric field. Okay. It states that the induced electromotive force, that is the line integral of electric field, around any closed surface is equal to the negative time rate of change of magnetic flux through the path enclosing the surface, which is known as the Faraday's law. So basically it means that a change in magnetic field can produce the electric field. And the fourth one is the line integral of magnetic field, that is the magnetic flux, magnetomotive force around a closed path is equal to the sum of conduction current and the displacement current through the surface bounded by that path. Basically, this is known as the Ampere's law, or we can say this is the modified Ampere's law. So this one is the Gauss law. Gauss law in electrostatics. And this one is the second Gauss law in magnetostatic. Third one is the Faraday's law. And the fourth one is the Ampere's law or modified Ampere's law. So these are the significance of Maxwell's fourth equations. Okay. So thank you. That's all for today.